How far is the nearest star? How big is the smallest particle? How high is the highest mountain? How deep is the deepest ocean? To measure, we compare. How fast is the fastest? How slow is the slowest? Tall, but not tall enough. Gaining weight, but not gaining enough. We compare all the time. Even our movement is in comparison to something stationary. Perhaps the desire to quantify led to the idea of measurement. From personal to community possessions, people measure all. The archaeological remains of early civilizations suggest that they planned and measured everything they built. The ancients, while looking for a measuring standard, were struck by the proportionality of their limbs and the uniformity of their articles of daily use. They used the distance between their elbow and the middle finger and the length of their foot for direct measure. Based on these basic units of direct measure, they developed indirect measures using ropes, rods, and poles. With these, they measured their purchases, their buildings, and even their animals, and even described in the ballad Prithviraj Raso by Chand Bardoi beautifully illustrates the prevalence of this system of measurement. Using local measures such as buns, gaj and angul, Chand Bardoi was able to guide the blindfolded Prithviraj to shoot an arrow at his captor. These ropes or poles, however, could not serve the precise requirements of, say, an Indus architect, as they were building grid-patterned streets, rooms, courtyards, and settlements after settlements with identical precision. It is believed that the fragment shell found in the Indus Valley to be a measuring scale. The 10 distinct markings appearing between two solid dots on this scale makes it, perhaps, a forerunner of the decimal or the metric system. Incidentally, this scale from the solid dot to the empty dot is exactly double the Babylonian Shunsi scale of 0.66 inches. Though the Indus Valley civilization got wiped out, its measure survived right down to the early British period. Among the various gaz measures prevalent then, the 33-inch Akbar Mahi gaz or the Indian gaz is exactly 25 times this Indus scale. References to the construction of Vedis or sacrificial altars in the texts of the Vedic age that historically succeeded the Indus civilization suggests the prevalence of a standard of linear measure. Its central unit, like everything else in the male-dominated Vedic society, was the Purusa, literally the man, based on a 6 feet high person with hands stretched upwards.
And the equivalent of a Purusha was a Vyama, the distance between the tips of the fingers of the stretched hands, which was equal to 120 angulas. The angula was the primary unit, and between the angula and purusha, there were other subsidiary units such as pradesha or span, which is equal to 12 angulas, and artani or hasta, which is equal to 2 pradeshas or 24 angulas. Then Vyayama or the total height of a person is equal to 4 arthanis or 96 angulas.
Vedic Hindus were perfectly aware of the fundamentals of measure. Thus we find in Markandeya Purana a table containing common multiple.
It is surprising that even at that time they conceived a system of very fine measure like Toshorenu, which consists of fine particles of dust moving in the air and which can be seen only when a ray of light enters the room. They also conceived the thickness of the tip of the hair and also that of sand particles. Thus, this table of common measure contained in the Markandeya Purana is very important, as we do not see any such system of measurement in the world until the introduction of the metric system in 1799. Measurement was following an evolutionary process in the other parts of the world too. The Anglo-Saxons of the 5th century introduced the system of the inch, the foot and the yard. The Romans followed another, using palm, cubit, fathom, pole and furlong. Inch was defined as 3 grains of barley, dry and round, placed end to end. A yard as the distance from the nose to the end of the middle finger when the arm was outstretched. A furlong was defined as the length of one furrow as far as a plough goes before it turns. Keen on legalizing the measure, the imperials as early as 11th century declared all weights and measures were to bear king's seal as proof of authority. As the British Empire spread, this system spread too. Based on physical differences, regional variations emerged. As empires grew and trade became global, the need for a global standard arose. In France, this need led to a search of an internationally agreed standard culminating in the meter. The story of the meter began in 1670 with the publication of Gabriel Mouton's book Observations Diametrorum Solis et Lunae Apparentum. Realizing the limitations of the human body as a standard of measure, Mouton perhaps for the first time suggested a universal standard. Taking the Earth's surface measure as the basic standard, he defined this unit, which he called the millia, as the length of 1 minute of an arc on a great circle. His idea, however, only remained an idea. The difficulty in accurately measuring the Earth's surface at that time prevented it from becoming a reality. It took a French Revolution to achieve that. French Revolution brought new ideas in every sphere. One such idea was to rationalize the confusing mass of weights and measures prevalent then. On the suggestion of Talleyrand, the French Academy of Science set up a committee with renowned mathematicians and scientists to look into this. Based on its recommendations, the meter was accepted as a unit of length. It was to be spelt M-E-T-R-E and not M-E-T-E-R, and was defined as the 10 millionth part of the quadrant of arc of meridian which passed through Paris. To assess the length of the quadrant, two French astronomer geodesists measured the actual distance between Dunkirk and Barcelona, a task that took them 7 years to complete. With the motto "For all people at all times," in 1799, France and its neighboring countries adopted the standard meter. If the French Revolution originated the idea and the newly formed Republic helped to define it, then it was the Napoleonic conquests of Europe that popularized it. In 1875, on the recommendations of the CGPM, the General Conference on Weights and Measures, the prototypes of the meter was constructed and distributed to the 20 countries that signed the Treaty of the Meter. To keep it precise, the standard meter was made of a corrosion-resistant alloy of platinum iridium. But as Earth is not perfectly spherical, the prototype, when measured at different places on the surface of the Earth, gave different results, leaving it not only short in length, but also different from the original definition. A standard measure which varied from place to place could hardly be accepted. Thus began the search for an ideal measure standard. Krypton gas found in the Earth's atmosphere provided the answer. The wavelength of a particular orange-red radiation emitted from the krypton gas was taken as the natural unit of length. The General Conference on Weights and Measures, CGPM, the international body which deliberates on these matters, standardized the multiples and submultiples of the meter. The metric equivalences of an inch, a yard, and a foot, too, were defined and standardized. With this was born the System International, or the SI. The System International not only standardized the other basic measuring units and their conversion factors, it also defined them. However, scientists such as particle physicists and astronomers still needed units which were beyond the CGPM multiples and submultiples. Their problem was how to express the dimensions of subatomic particles or to measure the distance between the Earth and the nearest star. Angstrom, a Swedish physicist after whom the unit of measurement of very small wavelength is named, provided the answer. The unit angstrom is used to express the diameter of the smallest particle. The distance of the nearest star can be given in kilometers but is better expressed in light years or parsecs. For all day-to-day transactions, the metric system is still the best approximation. But science and its application would require far greater precision and accuracy. Approximation can keep a kite afloat, but for an aeroplane to fly, its wing balance and design has to have a high degree of precision. From conception to design to formation, the process at work is precision of measurement. Some of the modern-day architectural wonders would never have seen the light of day but for the great advance in the measuring techniques. Can you imagine what would happen if the precise and delicate balance of these cables is disturbed? Lack of precision in measurements can cause a tilting of the balance which may not be in anyone's favor. Measurements, be they in shops or in laboratories, in the ground or in the skies, are not just there for convenience. They introduce a discipline, both in thinking and in living. Sometimes They make the difference between life and death.